Mergesort, another sorting algorithm. Yeah. And this one also very useful. So many ideas, very useful. Yeah. So let's study this new sort. C.1 Introduction to Mergesort. Yeah. First, let me describe a simple computing problem. Basic computing problem. Yeah. Very easy, yeah, but very useful. Merge two sorted arrays. Yeah. Given two arrays already, two ordered arrays. Yeah. But we need to merge these two to get a one bigger ordered array. So it's a very basic question. Yeah. So we want to find the fastest solution solving this problem. Yeah. All right. Given two ordered arrays, how to merge them to get an ordered array? Simple question. Yeah. All right. Motivation. Yeah. First, let me describe the background. So in our real world situation, sometimes we may need to do this operation. Yeah. So this merge operation. Yeah. Here, I want to describe a special question. Yeah. Interesting. Yeah. So you may not have a big chance to do it. Yeah. Yeah. But, sometimes you need to solve questions like this. Yeah. Why we need to consider this problem. Yeah. So here, I want to describe a very special problem. The question is how to sort a huge array. So if a given array is, because if the array is not too large, then, so you do not worry. Yeah. So you just, write your program, you load the data, so you sort it. But the question, now, the array, the data, is so, the amount of data, because your computer has limitation, right? Your computer, everyone, your computer it has limitation. Yeah. Can you imagine that sometimes the data, the amount of data is too large that you cannot load it into your computer memory? That situation. That could happen, yeah. Because in our many real-world applications, we need to process huge amount of data. Yeah. And in that situation, it's impossible to load all your data into computer main memory to do processing. Yeah. We know our main memory has limited amount of space, right? Yeah. Some of you may have 16 gigabytes RAM, right? 16 gigabytes, yeah. My laptop here, only 8 gigabytes. Yeah. 8 gigabytes already pretty big. Yeah. But even 16, some people may have 32 gigabytes. Yeah. Even that, yeah, there is a possibility the data amount is too big, so you cannot load it into all your data into your main memory, yeah, that RAM. Okay, yeah. In that situation, the question: you can find a way to sort that huge array? So let's answer that question. Yeah. Yeah. We can do it. Yeah. So we can do it. Yeah. Divide and conquer, right? So the title of this module, divide and conquer. So we want to apply divide and conquer to solve that problem. Yeah. So here, let me describe the whole idea. Suppose this line segment represents that huge original data. You cannot load it into your main memory at once. Yeah. So we have to break it into smaller subarrays. Yeah. So here, I assume I will break it into, several pieces, smaller subarrays. So each subarray, we can load it into the main memory. Yeah. So each small, subarray, we can load it into main memory easily. Yeah. So we can sort each one, right? Yeah, each one. The first one, loaded, sorted. Second one, loaded, sorted, yeah, and so on. So we can sort all these subarrays, yeah, one by one in main memory. That's the first round processing. Yeah. The second round, yeah, because our goal, we want to make the whole array sorted. Yeah. And you cannot load all your data. Yeah. So now we need to do our next round, because the first two subarrays ordered, yeah, so yeah, when we order them, we can do parallel computing if you like. Yeah, multiprocessor per, yeah. So now for the next round, can we merge the first two ordered arrays? Yeah, we know. All of them, all of the subarrays are ordered. Now, what do we need to do? We merge those ordered arrays. But when we do that, is that we need to solve this problem, merge two ordered arrays? Yeah. Every time we merge two adjacent ordered arrays to make the whole array ordered. But when you merge, you do not have to load all the data into main memory, right? Yeah. You can load part every time. Every time you can load part of the data and do the processing. The next time, another part of data, do processing. Can you do that? Yeah. So in that way, you can always merge two adjacent ordered arrays. Yeah. How to merge, we will answer later. Yeah. So here I just described. Yeah. If you can solve this basic problem, yeah, this basic computing problem, then you can solve this whole that problem, big data problem. That's huge array problem. Yeah. If you can merge, yeah, when you merge, you do not need to load all your data into the main memory. Yeah. So you can load, portion by portion, yeah, for each subarray, portion by portion. Then you can get them ordered. Yeah. So the detail, C.2, we will study that. Yeah. Yeah. So here you can see, sometimes, because in our current big data era, right? So now we are in the big data era. So AI, big data era. Yeah. So you may have a chance, in the future, you may have the chance, you need to process large amount of data, but you cannot load all of them into your main memory. So you need to load them portion by portion, okay, for processing. Yeah. All right. Yeah. Yeah. How to merge two sorted arrays. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements. Yeah. So here, let's consider this merge operation. Yeah. Here, we need to take advantage of the structured data. The structure ordered data, that's the structured data. How do we take advantage of the ordered data? That structure. Yeah. So let's recall. Yeah. At this point, we have learned 3 sorts: selection sort, bubble sort, insertion sort. Yeah. So we want to see if we can borrow some idea from these sorts. So which one could be used to solve the current problem? All right, yeah. So do not use any sort that does not make use of any order information. Yeah. So we want to select the sort that can take advantage of the order information. Yeah. Then it could be useful. Otherwise, if the sort never makes use of the order information, then we cannot use it to solve our current problem. Yeah. All right? Yeah. So let's look at a selection sort. For selection sort, if the input data is ordered or not, does it matter? It doesn't matter. Right? No matter the input data is ordered or unordered, you need to use the same number of comparisons, right, for selection sort. Okay? 1/2 n times n minus 1. Always this number. Okay? No matter what the input data you have. That's the selection sort. Yeah. For the bubble sort, does it any difference? Does it make any difference for the data ordered or unordered? No difference, bubble sort. Yeah. Same thing, 1/2 times n minus 1 for any given data. Okay? Yeah, no difference. Yeah. How about the insertion sort? We just learned in part A of this module. When the data is ordered, unordered, do you see the big difference in the efficiency function? Yes. This one, yes. Yeah. Why? Because if the data is ordered, you have the best case, big theta of n, right? If it is unordered, you get a big theta of n squared. Okay? That's a huge difference, right? Big difference. Yeah. So this tells us the insertion sort really takes advantage of the ordered data. That means we can borrow the experience from insertion sort, bring it here to solve our current problem. How about that? Yeah. That's the, importance. Yeah. So our old experience, very useful in solving our current problem. Yeah. All right. Yeah. Yeah, because think about, we have a nice property for the insertion sort. If the data is almost ordered, then insertion sort is the best sort. Yeah. In all possible choices. Yeah. All right. Yeah. Next, so let's look at the insertion step. Yeah. Yeah. insertion step. Yeah. So we want to start with the insertion step. Yeah. Then we try to, we want to see if we can modify that insertion step to do this merge step. Yeah. All right. Yeah. So here we take a different view on the insertion step. So why we take a different view? Because we need some new idea. Yeah. So we don't just want to repeat the insertion step. Yeah. So we want to modify the insertion step. Yeah. All right. Yeah. Here, let's look at a typical insertion step. The A array is ordered. Okay. Now we want to insert a key V somewhere into an ordered array. Yeah. So the details, implementation details, how to do it, right? Yeah. But here, can we imagine that single element V? It is just a one element array. Can we view in that way? So it's a special case. It is a single element array. That's special case. Okay? Yeah? Yeah. In that way, can we view this insertion step is basically, it's a special case of the merge step. Right? Merge two ordered array. That single element we treat it as an ordered array. Special ordered array. So we just merge two ordered arrays. Yeah. But the special thing is it's a one element array. But now we need to modify. This one element array, we want to make it multi-element array. Multi-element array. Then we just work on the merge operation. Yeah. So that's the connection. Okay? All right. Yeah. So that's the new interpretation. Two sorted arrays are combined to get a new sorted array. That simple. Okay? Yeah. How to do it? How do you do the insertion operation? Then we will do the similar way for the merge operation. Okay? It's a new view. Merge two sorted arrays for a new sorted array. So we need to focus on this merge step, implementation step. Yeah. So now we apply new merge view. Yeah. All right. So if you look at the insertion step, the data size k and 1, yeah, and the data distribution is not balanced. Yeah. K and 1 not balanced. Yeah. Balanced here we mean the data sizes of these two subarrays are very close. Very close. Then it's a balanced distribution. We know when we have a chance to distribute the data, if we distribute it in a balanced way, then we will get the best efficiency. Yeah. So that's what we call the balancing principle. Okay? All right. Yeah. So here. Yeah. So this unbalanced data distribution may cause poor worst case problem. The worst case, very poor. Yeah. So we want to avoid it. Okay? Yeah. So to improve performance for the worst case, now we want to take that balancing principle. Try to make two subarrays of equal size, yeah, to avoid poor worst case efficiency. Yeah. So C.2, let's look at it implementation details of this merge operation. All right. How to achieve balanced subarray split. Okay, yeah. So whenever we merge two subarrays, we make them of equal size. So here, because remember, we need to apply divide and conquer approach. So we have a divide step. At the divide step, then we make even split our data evenly. Then we get a balanced data distribution. All right. Yeah. Let me use this line segment to describe even split idea. All right. So for this whole array, we do divide and conquer. The first time when we split in the middle, somewhere in the middle. Okay. Yeah. Yeah. All right. So we get a two subarrays with almost the same size. Yeah. Depends on n is even or odd. If n is even, we get an even split. N is odd, one subarray has one more element than the other subarray. That's simple. So that's the first split. Divide step. Then imagine conquer. Okay? So here we delay the conquer details. You just imagine So eventually we will get each subarray ordered. But since we are solving this problem recursively, so we need to look at how to split each subarray. So for each subarray, we split in the middle. Okay, yeah. So the second round splits. Yeah. Then third round splits. Yeah. We'll keep doing the splits like this. Okay, yeah. Even split like this, all the way down to the last step. Yeah. What is the last step? Last step. Okay. Each subarray only contains one element. Then you cannot split anymore, right? Yeah. Each subarray can only have one element. Then you have to stop. Okay? Yeah. So the last round, when each subarray has one element, now you are ready to merge. So now you need to go back. Okay? You need to merge adjacent two ordered arrays to combine those subarrays to get larger ordered subarrays. Yeah. All right. So now, first round merge from the bottom level. Yeah. You just merge two adjacent subarrays. Next round, because your ordered subarrays become larger and larger, the array sizes, the sizes of those ordered subarrays become larger and larger. So the next round, you merge two ordered adjacent subarrays to get a larger ordered subarrays. Yeah. Then another round, larger ordered subarrays, and at the end, you merge the last two ordered subarrays to get a whole big ordered array, and you sort the whole big array. That idea. That's this new sort idea. Okay? Divide and conquer. Yeah. Yeah. So divide, easy, split in the middle. Yeah. Conquer, yeah. So you reverse your divide steps. Okay? Yeah. Merge two adjacent ordered arrays. So you can see, if we know how to merge two ordered subarrays, then we can solve this whole problem. The whole sort problem we can solve. Yeah. All right. Yeah. Yeah. Because in this way, we have a chance to avoid poor worst case. Why? Because we apply our balancing principle. We distribute our data evenly all the time, right? Yeah. So based on our balancing principle, we can avoid very poor worst case efficiency. Yeah. All right. So next we need to study the main step, merge step. Yeah. All right. So let's look at the merge step. Here I use diagram to describe the idea how to merge two ordered arrays. Yeah. We assume these two arrays ordered. Yeah. Now we do first comparison. Yeah. All right. We do first two comparisons. All right. First comparison. Yeah. We know A0 is the minimum of the first subarray. B0 is the minimum of the second array. Yeah. If we compare A0 and B0, what will we get? Yeah. We have a smaller element. We have a larger element. Yeah. Here, let me assume main 0 is the smaller of the two elements. Okay? Yeah. After the first comparison. After that, we know the smaller number, we can put it in place, right? Yeah. Suppose we have a destination array. Yeah. Let's imagine. Yeah. So we want to put all the elements in place in our destination array. Okay? But after the first comparison, we have this main 0 element and the max 0 element, the smaller one and the larger one. And we know the smaller one, the main 0, should be the minimum of all the elements, right? All the elements. Then, if we want to place it somewhere in the destination array, it must be the first element in the destination array, right? Because it's the minimum of the whole destination array. So after one comparison, we can put one element in place. Now, we need to look at the second comparison. For the second comparison, this max 0, we do not know if we can put it in place or not. So we need another comparison. Now here, let's assume max 0 is this B0 case. Okay? All right. Then, to find the next element in place, we need to compare B0 and A1. Yeah. Because A1 is currently the smallest element in A subarray after we remove A0. Yeah. Because we already put A0 in place. So we need to remove it from the current A subarray. Yeah. So next comparison, we need to compare A1 and B0. The smaller one, we call it min 1. And we can put a min 1 in place. just after the second comparison, we can put a min1 in place. Yeah. All right. Then the larger one, max1, then we need to compare max1 with another element. Yeah. Yeah. So we keep doing like this way. Okay? Yeah. If max1 happens to be A1, so the next element you need to compare A1, B1. A1, B1, and so on. Okay? All right? So if you do comparisons like this, every time when you do one comparison, you can put one element in place. That's simple. Okay? Yeah. All right. The question. What is the last element we put in place? Yeah. Last element we put in place, right? Yeah. Yeah. So here, let's look at the worst case. Yeah. Because if you want to answer the question, what is the last element we put in place? Yeah. We need to consider the best case and the worst case. Yeah. Here, let's look at the worst case first. Yeah. All right. The worst case, the last element, yeah. When you do comparisons, after your comparison, you put one element in place. And now you want to consider the last comparison to help you to put one element in place. That is this one. Okay? Because after you put this element in place, then you only have one element remain, then you don't need to do comparison, right? Only one element left, then you just drop it in place directly without any comparison. So for that observation, the second to last, you may need a comparison, okay? For the worst case, you need a comparison, okay? For a better case, you may not need a comparison. You can drop it in place, yeah. But because here we consider the worst case. So for the worst case, we need a comparison to put the second to last element in place. Now you can count how many total comparisons we need for the worst case, because we know for each element in place, we need one comparison. Each element in place, we need one comparison. Okay? Except the last one. And how many comparisons do we need to put all these elements in place for the worst case? Okay? Is it the total number of elements minus 1? Yeah. Total number of elements minus 1. Yeah. Because this last one we do not need to do comparison, minus 1. All right? Yeah. Before that, yeah, we have one-to-one correspondence. One element, one comparison. One element, one comparison. One-to-one correspondence. Okay? Except the last one. Yeah. All right. How many total elements do we have? Yeah. The number of elements in the first subarray, K. The number of elements in the second subarray, also K. K plus K, 2K. So we have 2K elements. And 2K minus 1. That's the answer. So for the worst case, the number of elements we need to merge these two ordered arrays, 2K minus 1. 2K minus 1. Okay? Yeah. So that's the worst case. Total number of elements minus 1. Okay. All right. So we complete the worst case. Next, let's look at the worst case for the general merge step. Yeah, because in the previous slide, A subarray, B subarray, they have the same size, K. But this time we want to consider the general case. A subarray, there are m elements, and B subarray, there are n elements. Yeah. And m and n could be different. Yeah. Where we have this general merge step, then the same analysis in the previous slide can still be used. Okay? Yeah. Every time we do one comparison, we put one element in place. And for the worst case, we do not need to do comparison for the last element. Yeah. Before that last element, we need to do one comparison to put one element in place. Yeah. So then, the number of comparisons should be the number of total elements minus 1. And the number of total elements, m plus n. So the answer for this general step, m plus n minus 1. So that's the general merge step. Yeah. Next, we need to look at the best case for the merge step. Now, this time, let's just look at best case for the merge, general merge. Yeah. Because it's pretty easy, so we can work on the general case directly. Yeah. Pretty easy. Yeah. All right. For the best case, we want to look at the special data for which we need to do the minimum number of comparisons. What kind of input? If you have such input, then when you apply this merge operation, you need to use the minimum number of comparisons. That's the best case. Okay? Yeah? All right? Yeah. So we can keep doing the similar step as we did before, but can you imagine a special situation such that at some point then you do not need to do further comparisons. You can put the maximum number of elements in place without comparison. Yeah. In our worst case, we can put one element in place without any comparison, right? Yeah. But that one number is relatively small. Okay. To get a best case, then you need to put more elements in place without any comparison. Can you imagine a special situation such that there are a certain number of elements you can put them in place without any comparison? Think about that special case. So here, let me use one special case. If the first element in B subarray is greater than all the elements in A subarray, what would happen? The first element in B subarray, B0, is greater than all the elements in A subarray. What would happen? When you do comparison, B0 beats every element in A subarray. Okay? Yeah. All right, so then you will put all elements in A subarray in place one by one. Okay? All elements in A subarray in place one by one with the same number of comparisons. Yeah. In A subarray, there are m elements. So you use B0 to beat all of them. But when you do that, you need to make m comparisons, right? M comparisons. But after these m comparisons, the remaining elements in all the elements in B subarray, you do not need to do further comparison, right? Yeah, because these elements are already in order, and their positions should be after the positions of all the elements in A subarray. Okay, so you can copy them in place in the destination array without any comparisons. Think about that. Yeah. In that way, the number of comparisons you need is this number, n. All right? But these two numbers, m and n, you do not know which one is larger, which one is smaller, right? You don't know m larger or n larger. Yeah. So if n is smaller, do you want to put the elements in B subarray in place? Yeah. If n is smaller, n could be smaller, right? Smaller than m. Then you do the other way around, because you want to make A0 beat all elements in B subarray. In that way, A0 would force all the elements in B subarray in place. Okay? After that, then you just copy all the elements in A subarray in the remaining positions in the destination array. Okay? So in that case, the number of comparisons you need is n. And because we assume n smaller than m, so we get a fewer number of comparisons than the previous case. So now our conclusion. So here, the strategy, we try to exhaust one of the two arrays as early as possible. So you just imagine a special data input for which you can exhaust one of the two subarrays as early as possible. So the first element of one of the two subarrays can beat all the elements in the other subarray. In that way, in that assumption, you exhaust one of the two subarrays as early as possible. Right? Yeah. But here you only have two cases to consider. Which subarray you want to exhaust? Shorter subarray. Shorter subarray. Okay? Yeah. So the answer for the best case efficiency, the minimum of m and n. So we get two formulas. The worst case formula, m plus n minus 1. The best case formula, minimum of m and n. After this discussion, we solve the merge step completely. Okay? Yeah. Completely. This is the standard merge step. Yeah. Here I emphasize standard merge step. Yeah. Because sometimes some students imagine a situation. Yeah. So later in our homework assignment questions, because I will ask you the best case, worst case. Especially when I ask you the best case. So based on my experience before, many students, here I see some chat messages. So I will check it later. So when I ask you the best case, some students give me the answer. Some students give me the answer 1 because they compare B0 with the last element in A subarray, and under assumption B0 greater than AM minus 1, then you only need one comparison. You can get all your data ordered. Yeah, that's correct. That's correct. But that's not the standard. So when I ask you, we run standard merge step. Some people may ask, so why we cannot modify, in that way, right? Yeah. Yeah. So although you can, yeah, but you need to consider all the cases, right? Yeah, all the cases. Yeah. 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 So if you do in that way, then do you want to do the reverse way, right? Yeah, yeah. Because for that best case, yeah, that's one. But if it's not the best case, do you want to do the reverse way, right? Yeah. Yeah. So that question, you need to consider all the possibilities and see if that way is better or not. Okay? Yeah. So, but that discussion could be very complicated. Yeah. So here, when we talk about, so in the homework questions, when we talk about merge operation, merge two ordered arrays, we mean we need to use our standard merge step. Okay? Yeah. 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 Otherwise, yeah. So you have different options. You may do, yeah. Question, Joe?
So you will always start by comparing the first elements of each array?
We start with first element. Yeah. Both first element. Yeah. Not the last. Yeah. Yeah. Not the last. Yeah. Yeah. Right. For the last one, yeah, because to get a clear idea, if you do the last one, if you get a better average case, yeah, here, let's assume we want to, yeah, because when we compare two merge algorithm, which one is better, we should compare their average case efficiency, right? Which one would give us better average case efficiency? Yeah. So probably I can make a simple questions, ask you to compare the average case efficiency for those two ways. And let's see which one has better average case efficiency. Yeah, so that would be interesting. Okay, all right, yeah. Last first, first last. Okay, yeah, all right. That's pretty interesting. Yeah. All right. Yeah, here, just let you know, when we answer our homework questions, we use this standard merge step operation. Yeah. Oh, let me check the two chat messages if I have anything. Yeah, all right, yeah. Oh, yeah. What's that? Yeah, unmuted. Oh, I unmuted. Oh, okay, I don't know. Yeah. I unmuted by accident. Yeah, let me get it out. I need to mute. Unmuted. What's that? Unmuted. Is it this one? Or this one? Is it better I mute microphone in that desktop, the station? Is it better I mute it? No echo. Oh, great, Justin. Thank you. Yeah. Yeah. Sorry. Yeah. Sorry. It's better. All right. Doesn't realize. Oh, she unmuted. It's better. Oh, unmuted. Okay. Oh, yes. All right. Yeah. So here, look at the participants. Oh, Tuller. Yeah, Tuller, you unmuted. to the, I can click, yeah, right. Okay, yeah, she unmuted. Okay. Lee Ann also unmuted. Yeah. All right. All right. So let's continue. We have 15 minutes. Yeah. All right. So now we move to the next topic. Yeah. Efficiency analysis. Yeah. We have 2 slides. So let's complete these 2 slides in C.3, efficiency analysis for Mergesort. All right. Okay. All right. Yeah. Derive recurrence relation. Now, how many comparisons? If we want to sort the whole array, so because we need to do many merge steps for the best case and the worst case. Best case and the worst case. Here, let's consider the worst case. Because the worst case, if we know the number of comparisons for the worst case, then we know we can solve any case with at the most that many comparisons. Yeah. All right. So let's estimate the worst case efficiency. Divide and conquer. But this time, we want to derive that recurrence relation. Yeah. T of n, split in the middle. So you get 2 subarrays, each subarray approximately 1/2 of the data size. N over 2, 1/2 of the data size. Okay? Yeah. So then you conquer. Yeah. When you conquer, we apply the recursive function. That's the conquer. Okay? All right. So that's T of n over 2. That's the conquer step. Conquer step. But after we conquer each subarray, we need to merge 2 ordered arrays. And when we merge 2 ordered arrays for the worst case, we use the worst case formula. The total number of elements in 2 subarrays minus 1. Yeah. So here, based on our worst case formula, we should use n minus 1, but remember this minus 1 is very small. For simplicity, we just use n. Okay? So we drop that minus 1. Yeah. Just the one difference. Yeah. Okay? So we use n. Yeah. All right. Then we write this recurrence relation. The base case. If the element has 1, we do not need to do any comparison, so it's 0. When we have 2 elements, we need to do 1 comparison. It's 1. Okay? 2 base cases. After that, we get a recurrence relation. T of n, in order to sort the whole array with T of n comparisons, then by divide and conquer, we need to sort each subarray. But we need to sort 2 subarrays. So that's why 2 times T of n over 2. After that, we need to merge 2 ordered arrays. The merge step, for the worst case, we need n minus 1, but here we just use n. Okay? We drop that minus 1. Okay? All right. So we get this recurrence relation. Next is, we want to solve this recurrence relation to see what is the function of T of n. Yeah. All right. So, in order to solve it, we take the strategy. Consider a simpler case. There are many cases, right? Yeah. Yeah. A simpler case, here we look at the n even and odd. N is even, that's simpler, right? N is odd, harder, so we skip, okay? All right. So n is even, but because we need to do recursion all the way, all the levels, we always want the data size even, then the best we can get, n is power of 2. Then we can always get an even number, right? Before the last step. Before the last step, okay? All right. Then we can simplify our recurrence relation. T of 2 to the k equals 2 times t of 2 to the k minus 1 and plus 2 to the k. Yeah. Because in this way, all the denominators are gone. So we do not need to deal with the denominator. Okay? Yeah. All integers in our formulas. Yeah. But how to solve this new recurrence relation? Here, we need to do a special operation. Transformation. And this time, we need to do division. Division. Appropriate division. So why? Because after we use the division method, divided by 2 to the k, both sides, then we get a similar structure. At the left-hand side, t of 2 to the k over 2 to the k. This structure. Okay? Right-hand side, you can see t of 2 to the k minus 1. The exponent number is 1 less. Yeah. Over 2 to the k minus 1. Yeah. But the structure, they have the same structure, right? Yeah. Same structure. Yeah. Yeah. If we can do the transformation like this, then it's easy to solve. Yeah. So with a similar structure, let us define a new function. Yeah. So the new function is we let this g of k, g function equals that fractional form, t of 2 to the k over 2 to the k. Because after you introduce this g function, we can make the recurrence relation much simpler. Yeah. Now our recurrence relation, after the substitution, the new equation becomes g of k equals g of k minus 1 plus 1. That looks much simpler, right? Yeah. All right. And this recurrence relation, we can apply it many, many times. The next round, so here, the base case. Yeah. So if you make a k equals 0, right? K equals 0, 2 to the k equals 1. So g of 1 equals t of 1 over 2, right? Yeah. T of 1, sorry. Oh, sorry. T. Yeah. What's that? Oh, yeah, sorry. G of 1. G of 1, that's T of 2. Yeah. Right? Because G of 1. Yeah. So 2 of 2. T of 2 over 2. So that's 1 over 2. Yeah. That's this number. Okay? Yeah. All right. Then we apply this function the second time. It becomes g of k minus 2 plus 2. Yeah. Because this g of k minus 1, it equals g of k minus 2 plus 1. Okay? So 1 here, 1 plus 1, you get a 2. You get 2. Okay? Yeah. All right. But we need to keep doing the iteration like this. Yeah. Keep doing that. Yeah. The questions, when we keep doing iteration like this, how can we keep track of the data? We may get lost, right? So here, we are afraid we get lost. Okay, yeah. But how to keep track of our data? Remember, I talked about one special method in our first lecture. Yeah, that's the invariant property. Yeah, invariant here. What's the invariant? Size plus constant. Yeah. So look at the size. K minus 2 is the size number. The constant is 2. K minus 2 plus 2, that's K. Yeah. K minus 1 plus 1, that's K. The sum of these two numbers, it's a constant, it's constant K. Okay? All right. We use this invariance to help us keep track of the data. So then we do iterations all the way down to the bottom. The last equation, g of 1, the data size here is 1, but the constant part should be k minus 1. Why? Because 1 plus k minus 1 should be this invariance number k, right? Yeah. So in this way, yeah, we can get this last equation. Last equation, because g of 1 is 1/2, so we get a k minus 1/2. But that is g of k. Our goal, we want to get a t of k, a t function. Yeah. Yeah. So this t of 2 to the k over 2 to the k equals k minus 1/2. Yeah. But we want to use the variable n, not a k. Yeah. K is the intermediate variable, yeah, but not our original variable. So we want to write the t function in our original variable n, not the temporary variable t, k. Yeah. All right. So here let's update. Yeah. T of 2 to the k equals k minus 1/2 parenthesis times 2 to the k. But 2 to the k is n. 2 to the k, n equals 2 to the k, and the k equals log n, log base 2 of n. Okay? Yeah. So then we get a t of n approximately equal to n times log base 2 of n. Approximately, yeah. But here, you may argue, because we just consider n is a power of 2, but in our this formula, n is not necessarily power of 2. Yeah. Yeah. But here, we use the special case, power of 2, to help us get this one, get this. Can we make a guess? Right? Can we guess? So treat this as our guess. Then we can verify it, right? After we make this guess, we can verify it. Okay? Yeah. Yeah. Then we know verification is always easier than discovery, right? Yeah. Discovery, when you discover a new formula, it's hard. But if someone gives you the formula, you only need to do verification, then it's much easier, right? Yeah. Here we treat. So this one is our, guess formula. The next step, we can do verification. Yeah. Yeah. Here I skip that verification. Okay? Yeah. Yeah. Here I skip that verification. Here our conclusion is this t function is approximately equal to this n log n. Okay? Yeah. That's the reason. Its worst case is n log n. Okay? Worst case is n log n. Yeah. And you may ask, what is the best case? Right? What is the best case? Best case, remember, we have a best case formula. For the best case, we need to change that n to n over 2. We change that n to n over 2. So what's the best case? Yeah. And for, if you change n to n over 2, that's the best case. Okay? All right. Can you use the same way? Yeah. So we only need to modify our current method slightly. Yeah. Can you apply this, similar way? Yeah. This way, and you estimate T of n. Right? Yeah. Yeah. In that way, you will get 1/2 n log n. You just get a coefficient 1/2. Okay? 1/2 n log n. So the best case, worst case, all in this category, big theta of n log n, right? Both best case and worst case. Best case plus worst case. Okay? Yeah. All in this category. The coefficient is different. Best case 1/2 coefficient, the worst case 1 coefficient. Okay? All right. So after that, then we complete our merge sort. Okay? Yeah. We complete merge sort. All right. Yeah. Yeah. So the next time, part D, quick sort. Yeah. So we will do the quick sort in part D of module 4. Yeah. So then we will complete module 4. Yeah. All right? Yeah. That's it. Yeah.